Okay, what is this? Well, what I've got is a pump pumping out almost all the air in this tube. There's a little bit left. There's a little bit of gas left. And I've got a big electric field from this little sharp tip on this side to this sharp tip on, or this plate on this side. So what happens is that it sets up a current. The electrons are ejected from that end and travel along the length of this tube all the way down to the other end. As they travel, they're accelerated by the electric field that exists between those two ends, and they end up colliding with residual air molecules in the tube. What happens then is that the electrons that are traveling, these free electrons that are traveling, knock one of the core electrons out of an oxygen atom or a nitrogen atom. And what you're seeing is that nitrogen atom electron decaying back down to its lower shell, giving off this purple glow of light. It's a fluorescence. The first electron that's trying to travel along and get to the other electrode, or it's accelerating the electric field, knocks out another electron in a collision from a nitrogen atom. That electron decays back down to its original S shell and gives off a photon in the purple. Okay, and that's what you're seeing as this current goes through. But I look at this and I don't really know which direction the electrons are going in, or even if it's the electron current that we're seeing. I'm going to take this magnet now and put it next to this current. And I want you to see what goes on here. What's happening?
It's arcing.
Notice as I flip the magnet over, I can change the deflection of the current. So clearly there's a force on these electrons moving in the tube because they're in a magnetic field. The field lines actually come out the side and back around, so these electrons are seeing a field towards you in this direction, but notice they're deflected upward. Their velocity is this way. The field is that way, or that way. I'm not sure because I don't know the magnet. We can figure it out in a second. But the force on them is upward. Right? You see that? Now, I can switch the polarity on this. Let me see if I can get a good geometry where I'm not standing in front of what I'm trying to show. You see what happens? What's happening? Instead of being forced down, they get forced up when I switch the polarity. It goes back and forth. Why? I'm changing the direction of the electric field. So the electrons are traveling in opposite directions when I do that. Right? Because the electrons are always accelerating against the electric field. If my electric field is that way, the electrons are traveling that way. If my electric field is that way, my electrons are forced that way. So as I swap the polarity, the sign of the potential, the electrons are traveling in different directions, and therefore when I see a field, say this way, if the electrons are traveling that way, I would get a QV would be that way, be that way, be forced up. If I swap, then I get a force down, because now my velocity changes direction. Yes?
So are these just a bunch of free electrons, or is this like electrons in a gas?
Well, the gas, the reason I got the pump going is so that I have very low gas pressure here. If I allow, I'll show you in a second when I let gas back in, there's too much air in the way. The electrons will undergo a lot of collisions and just simply lose all their kinetic energy too quickly, and you won't see the glow. So I've got to have low pressure. I have to have some residual pressure in there in order to have that look.
So why purple? Is that just because of the velocity of the electrons putting off that wavelength, or is
No, purple is simply because I've got nitrogen gas left in there. And nitrogen, right, I'm talking about the quantum levels of the nitrogen atom now. And so what we're doing is we're kicking out electrons out of a particular shell, electron shell, and then they're falling back in. That process of falling from the continuum level down into a quantum bound level is a particular wavelength of light. It's quantized. So you see a particular color of light. And it happens to be in the purple. If it was a different gas, you would see a different color. Yes?
Would it increase the battery size? Would it increase the brightness?
Yeah, I mean, you'd probably see a brighter signal if I was able to get a larger voltage.
Is that how neon lights work? With different gases make different colors? For the
Yes,
sun?
exactly. And this is basically the process that you're seeing in the neon light. And that's why you hear that buzz. What you're hearing is the transformer buzz, right? That 60 cycle noise. And if you bring this guy close to the transformer, you can feel the 60 cycles in your hand.
Oh, wow.
You want to try? Come on out. Here, come on. You said, oh wow. Come on and feel it.
Where's the lab?
Just bring it over here.
Oh.
And you can feel the magnet oscillating at the 60 hertz because the transformer's there and you feel it. All right, so let's let a little bit of air back in to show you that process. See what happened now is instead of the potential drop happening between here and here, it's happening between those two electrodes, and we're simply getting a spark effect.